Well, let's invite. We should sing in the morning. Do you know any song about good morning? A good night? No, 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 not now. Well, good morning, everybody. We're going to start the last plenary section. I know that the climate is good to stay at home, and it's the last day. Everybody's a little tired, but we have wonderful speakers of this last plenary section. So I appreciate you came. And as you know, there is a link for seeing all the plenary sections of our conference. So we're going to send again. The first day I announced, but maybe you don't have. So we're going to send it by email, and you can send it to friends if they want to see. Okay? All right. So today we're going to start the first plenary section, and that is Professor Yakovlev. He is from United States. He belongs to many departments there, and he does a wonderful work on light interaction with almost everything we know, including living stuff. And I'm sure that we're going to have a wonderful talk about seeing life in a new light, from simple physics to quantum enhanced imaging. Wow, that's a very attractive topic. So, Vlad, please.
Okay, thank you very much for the introduction, and thank you all for coming here today. So I realize that it's the first talk of the last day of the conference, and typically that's the time when everyone is silent, the audience is empty, okay, also, but I don't see it this time, and I hope that you will be not silent at the end of the talk. So first of all, so I want really to thank organizers to give me this opportunity to talk to you today about some of the work that we are doing at Texas A&M. And of course, I want to start this also with acknowledging two very important people. First one also is sitting here on the first row, Professor Banyata, who did an absolutely fantastic job in organizing this conference. And the second person also is Marlon Scali, who is very inspirational for my work and for this conference as well. And by the way, also in less than 1 month, he's celebrating his 85th birthday. So I'll just want to extend my happy birthday wishes to him. So the outline of my talk is relatively straightforward. So after a short introduction, I will try to motivate you with why we are doing what we are doing, and then I will introduce you to the main topic, Brillouin spectroscopy, which has been around for more than 100 years, but still also people are asking me questions, so what it is, and things like that. And then I will conclude with the ideas of how we can use quantum imaging to enhance biological imaging, and then I will summarize. So before I begin, also I just want to acknowledge my hearers, also members of my group, past and present. So there's a really very productive team of young people, also, and they are doing extremely good job and success in their life. And above their heads, you see also all these logos, basically reflecting those fellowships that these guys acquired. So my research is focused around several areas. In biophotonics, I'm mostly interested in sensing, imaging, light-tissue interactions, and therapeutics. And we've done also lots of work not only related to Brillouin spectroscopy, but also fluorescence imaging. So we are also looking at the ways how light and electromagnetic radiation in general interacts with biological tissues. And we are doing lots of work related to biological sensing, trying to understand also biomolecular interactions both in vitro and in vivo. And of course, we are trying to use light to induce some therapeutical effects like treating infections and cancers. So the motivation from my work comes from NIH roadmap. So NIH, National Institute of Health in the United States, also is very pragmatic, and so it has its own customers, and those customers are medical doctors, and really also what medical doctors want is to diagnose and treat diseases. And also it's a very general task, but it's also a very complicated task because diseases are different, and we want to understand all the pathways through which those diseases are developing. And for this, you need ultimately those tools which are capable to look at molecular interactions at atomic and molecular scale. So it's a very difficult task. And really also, if you look at the medical imaging toolbox, you'll see that almost everything is there. And the problem is that there is no microscopic imaging, and there is no affordable imaging outside the ultrasound imaging. So really, also, our goal is to help physicians in diagnosing and treating diseases. And one of the best examples that I can pull from my own experience is this experience in dental office. So each year we go for for dental exam, and they take X-ray pictures of it, and then there is always a question, okay, well, so is there a cavity there? So to drill or not to drill? So, and apparently, also there is a very interesting and very simple solution using optics. Because if you have a cavity there, so that means that there is some bacterial infection. So bacterial infection means it's metabolically active, and you can actually detect it using fluorescence. So very simple idea. So if there is fluorescence, there is metabolically active bacteria. So if there is no fluorescence, also there is no bacteria. So moreover, you can quantify this by using a very simple device, okay, also, which you probably can build, say, on your own for less than $50. So it's just a simple light source and photodiode, and the only thing that you need is just to digitize the photodiode reading so that you can get a quantifiable measure of how strong or how weak is the metabolic activity. And there are multiple benefits of doing this, and I can point you to that. It's 90% accurate as compared to X-rays. And of course, okay, well, so this thing can cost you only $50-$100. So it's really okay, well, so it's a good replacement for this X-ray machine. So this is like official motivation for doing this. Also, kind of an official one, okay, also, and Barry Walker, okay, also my former colleague and friend, okay, also asked me to put this slide here, okay, also, is what Richard Feynman says. Physics is like sex. Sure, it may give you practical results, but that's not why we are doing this. So it's basically, also, it all comes down to our internal self, okay, also, so why we are doing what we are doing. I was fascinated by optics from my childhood. Actually, so when I was in high school, I was interested in doing astronomy. I built my own telescope. But of course, okay, so I can't compete with those telescopes. And this is just an example of how Crab Nebula looks like in different parts of electromagnetic spectrum. So this is something that motivates you because really, okay, so you see all these different pictures, and they're all colorful, they're all beautiful, and you want to do something like this, but for biological systems. And really, okay, so when I was in middle school, I actually hated biology. So really, okay, so when my biology teacher asked me to look at the cells, so I saw something like this, okay, so and I said, that's it. Okay, so that's what you can see with this microscope, which was at that time was very expensive. Yes, of course, you can put some additional contrast there, and you can enhance some parts of the cell, but it's still also not as informative as we want to see those biological features. We want to understand not only also the anatomical structure, we want to understand their function, and that means that we need new contrast mechanisms. And imaging is all about contrast. So just look this way, okay, so when you choose bananas, you choose them by color, right? Okay, so you don't choose this green one, okay, so you don't choose this black one, so you choose somewhere in the middle, okay, so which is considered to be the better ones. So the same thing with meat. So you choose this one, and you try to avoid this one. And of course, during COVID, we learned that we don't necessarily have to look in visible light. We can use the other parts of the spectrum to get this contrast. In this case, we can get the readout of temperature so that we can see if someone else is sick. So biology is very sophisticated. So fluorescence markers are always used to provide high contrast, and really it goes almost to perfection. You can see single molecules. So this is the work that I've done almost 20 years ago, back when I was doing sabbatical in Japan. So you can put multiple labels and image different with different colors, different fluorophores inside your cells and tissues. So it works great. But here's a problem. So the problem is that labeling, tagging requires that you put some biconjugate molecule, and while this technology is well developed on the chemistry side, and Nobel Prize was awarded recently for the click chemistry, so there are multiple problems which we have to avoid. So first of all, so we want these molecules to be small, non-toxic, don't affect structure and function, and of course have efficient emission and don't be phototoxic. So let's take a simple example. So we want to take like cadmium sulfide or cadmium selenide nanoparticles, which are known to be very strong fluorescent emitters, but we can't use them right away. So cadmium is toxic. So we have to surround them with something protective. So then we put a conjugated layer. So then we put additional molecules, and all of a sudden, so we get something like this, and this is your new construct, which is going through rather crowded cellular environment. So obviously, it will affect the traffic, cellular traffic. It will affect function, and it will not last for a long time, just because phototoxicity effect at the end will take over. So alternative is use endogenous markers. So that means that fluorescent molecules which are already there, and there are not so many of them that can emit fluorescent light, but we can use them for diagnostic of cancer and metabolic activity. But at the end, we still want to get out of those markers, fluorescent markers, because at the end, you get phototoxicity. And then brings us a very important philosophical question. So what is life? So many people just silently attribute this question to Schrödinger, who gave a course of lectures in 1943, and he had a book on this subject. But really, this question goes well beyond that, and the most comprehensive answer I found in Nikola Tesla's statement. He says that energy is everything that everything can be in. To understand the surrounding universe, you basically only need energy, frequency, and vibration. So it was kind of extended later by Albert Einstein, who was first talking about energy, but at the end, he concluded it, saying that everything in life is vibration. So basically, that's what is my talk about, is vibrations. But typically when we talk about vibrations, we talk about molecular vibrations, and it's a really good tool because infrared spectroscopy and Raman spectroscopy and elastic light scattering on these molecular vibrations, so they provide us with chemical contrast, so which we can use for analysis of tissues, molecular structures, and many other things. But the problem is that chemistry is not everything. So most of us are physicists, and we understand that physics is probably more powerful than chemistry. So, and in particular, we are looking at mechanical interactions within our cells and tissues. And believe it or not, people realize that mechanical interactions are extremely important. And in particular, also, it's very important to understand the stiffness and viscosity of those biological tissues. And stiffness is actually also not only important for biology. So like, for example, also we go here into the steakhouse, we enjoy our great steak, but we don't quite realize that experienced cooks, when they want to see if the meat is well done, also they just actually press their fingers against the meat, also, and by looking at the stiffness of it, so they kind of get to the point when the steak is ready. So it's also good for agriculture, and this was actually the first time I got on the national TV, also through my work with Kazakhstani University. And of course, also Brazil and US very high on oil, and for extraction of oil, so viscosity and stiffness are also of great importance. But it's even has a great importance for biology. Let's take carcinogenesis. So basically, we're trying to understand how do we get cancer. So if we just have one single mutation, so it's really also not a big deal, also because your immune system is supposed to be strong enough to take care of this. But if it's not, those cells start to proliferate, and at the end we have cancer. So this is just a very basic diagram. But we have to realize that those cells are not developing by themselves. So they're always surrounded by these extracellular matrix, extracellular medium, ECM, and interaction between these extracellular matrix and cells is what ultimately governs these cancer development, these cell migrations, so how they metastase, and so on. Unfortunately, we still have very poor understanding of how it happens, and I'll show you some of the ideas that we are currently developing in this area. And I always point out here that microscopic and macroscopic properties are not the same. Because typically the way we diagnose cancer is we're looking at the big tumor, and this big tumor is typically stiffer than surrounding tissue. So this is basically also how it's advised for women to look for the signs of breast cancer and so on. But if you take just isolated cancer cell and measure its mechanical properties, so you can do it using, for example, atomic force microscope, so you'll find out that those cells are actually softer than your normal cells. So here you see also there's a gentle balance between being softer on a microscopic scale and stiffer on a macroscopic scale. So another interesting biological problem is related to morphogenesis. Just think about this. We all came from a single cell. So we all started from a single cell, and all of a sudden, also we have 2 hands, 2 legs, and only 1 head. Why it's so? So for a long time, so once again, people thought that it's all due to chemical reactions, but apparently mechanical properties play a crucial role in this cellular differentiation, and this is why we want to understand these properties as well. So I hope that I motivated you enough so that we can actually look it up and see, also, boom, so we have a technology gap here. So on a larger scale, we have ultrasound imaging, but it only goes to millimeter scale. So we can also use optical tweezers and atomic force microscope, but it has very good spatial resolution, but you need like this immediate contact to those cells and tissues. So it's really not good, also if you want to do 3-dimensional imaging. So basically, also this is where Brillo microscopy comes into play. So this is a kind of a timeline of Brillo microscopy. So we typically attribute this to Leo Brillo. In 1922, he wrote a paper which suggested that light would be inelastically scattered in the presence of acoustic vibrations in the medium. So in 1980s, 1970s, at the end of 1970s, so there was the first application of Brillouin microscopy to biological systems, but only about 15 years ago, the group at MGH pretty much restarted the whole field by showing that the current state-of-the-art technology is able to do this efficiently and probably clinically significant. So for a long time, okay, I was showing this slide, okay, until my grade student at that time, okay, he was upset that, okay, some Americans did this first, okay, he found a paper done by Chinese group, okay, which showed the effect of low-frequency phonons for biological functions. Well, so for a long time, I was showing these slides, okay, in this modified version, until I finally got this paper, okay, is published in Chinese journal, and I found out that the true motivation from this work, they found from original Russian paper published in 1967. So basically, okay, at this point, okay, I couldn't find any earlier references, so I would say that 1967 is the time when people realized that those low-frequency phonons are important for understanding biological systems. We typically in US call it Brillouin microscopy. In Russia, okay, they don't call it Brillouin microscopy, okay, they call it a Mandelstam Mandelstam spectroscopy. But if you have to be politically correct and historically correct, you would call it Brillouin-Mandelstam growth spectroscopy. So essentially, okay, what Leah Brillouin suggested is what we now call stimulated Brillouin spectroscopy. So basically, okay, acoustic wave is already in the medium, and you scatter light off this. So Leonid Mandelstam in 1926 developed a theory for spontaneous Brillouin, okay, which means that there is no acoustic wave in the medium, and everything happens on spontaneous fluctuations, either entropy or temperature, and that results in this Brillouin spectroscopy. But the real hero here is Evgeny Gross, who in 1930 also performed a revolutionary experiment, which allowed for the first time to demonstrate these effects and to see this tiny frequency shift which is induced by these acoustic waves. So essentially, what we will be talking about is this Brillouin shift. So just the important part here is that it's proportional to the square root of longitudinal modulus, and this is probably the most important part that you need to remember, okay, through the rest of my talk. So essentially, okay, if I go to the details of spectroscopy, we're looking at this Brillouin peak, okay, this is Stokes, this is anti-Stokes. We're looking at Brillouin shift, so which is proportional to the real part of viscoelastic modulus or its stiffness. And if we're looking at the line width, so we're essentially measuring attenuation of these acoustic waves, and it's proportional to the viscous part of the modulus. So in one single optical measurement, which you can do with diffraction limited to spatial resolution, you get two quantities in the same time. So this is why, okay, it's such a great spectroscopy. And fast forward, okay, the Garden in 2022 called this the one of the most important scientific stories of the year. So now we can do, well, so imaging from cellular level to almost like, okay, whole animal level, okay, so we can do artificial and natural biomaterials. We can do pretty much everything now, okay, and the reason why the Garden, okay, called it the biggest stories of 2022 is because it's the only technique which allows you to do those measurements non-invasively, so that means that you don't disturb your sample, and in 3 dimensions, and with microscopic spatial resolution. So what do you need to do that? So essentially, okay, well, so if you compare Brillouin with Raman spectroscopy, a couple of things that you might notice. It's the typical frequency shift. So frequency shift in Brillouin spectroscopy is orders of magnitude smaller than Raman spectroscopy. So that means that you need much better spectral resolution in order to characterize this peak. So, and of course, okay, well, so the contrast is different. So in Raman spectroscopy, you imaging chemical bonds. So in Brillouin spectroscopy, you're imaging sound velocity and sound attenuation. So that at the end gives you those two moduli, which you then use to display and to make those beautiful images, which I will show you later. So to do this, you need a narrow band laser, you need high resolution spectrometer, and you need some way to suppress your elastic scattering in order for this to happen. So when we first started doing this, okay, well, so we realized that also there's lots of potential to utilize what is already available for optical communication market. So that's what we did. Okay, well, so we took dyed laser, amplified it using fiber amplifier, and using second harmonic, we converted to either 532 or 780 nanometer light, and she then used frequency locate to either molecular or atomic absorber, and we get everything that we need from a laser, narrow band, lots of power, beautiful mode, so very high stability. So how do we do all these spectroscopy measurements? Because typical spectrometer also has a resolution maybe 1/10, at the best 1/100th of nanometer, and it's still also 10, 100 times less than we need. So Newton Gross in 1920s suggested that if we use a set of interferometers, so you can actually look at those Brillouin spectra, and those are the first Brillouin spectra that he published. So in 1930, he realized how to do that, and believe it or not, we're still using the same type of approach to do it these days. So of course we do a little bit of modification. So he used a system of 30 interferometers. Now we're using just only one, but it's a very special one. So it's called the virtual image phase array. So what it is, also beyond the fancy name, is just a tilted attalon, so which disperses light, and then after focusing it with a spherical lens, so you get your spectral dispersion along the line, and you can play with this. So you can put 2, 3 or whatever you want, and disperse it in 2 dimensions. So this is typically how it looks like. So remember that it's more than 10 years ago, so we went way far better, from this. But so this is your elastic peak. So this is Stokes, this is anti-Stokes. So it's clearly seen, so looks great. Looks great only when you have a transparent media. But immediately when you put scatters there, so you're in big trouble. And biological tissues typically don't propagate light quite well. So that's why we're not transparent. So my student, she decided to mimic this effect, and just use a coffee cream, to make this DMSO solution a little bit less transparent. And you see, all these wonderful peaks that we saw here. So they're kind of buried in this scattered noise, produced by light scatter. What can we do about this? So essentially what we need to do is to get rid of this elastic scattering, so which happens exactly at the same wavelength as the excitation wavelength. So for this, we just go back to atomic molecular optical physics, and we realize that if we take either a molecule or atom which has a strong absorption line just to add our excitation wavelength, so we can suppress it through absorption. So it's a kind of absorption notch filter, and we can only see Brillouin scattering. And this is basically also how we did this. And now we can routinely take Brillouin spectra at millisecond scale. We can have both 780 and 532 nanometers. 780 nanometers works great with rubidium atoms. LPHYS'24 works great with iodine molecular weights. Okay, so basically, okay, well, so system is done. Okay, well, so I was cheating a little bit. So I was cheating, okay, well, so in the sense that I was constantly talking about viscoelastic properties, but I didn't tell you the most important part. Because in parallel microscopy, we are not measuring your traditional low-frequency modulus, so the one that you typically experience, okay, by stretching your spring and compressing it. We are measuring it at high frequency, at gigahertz frequencies. So it's somewhat different. And you can see that, okay, well, so we can actually characterize our materials using traditional ways, okay, well, so we call it storage modulus and loss modulus, and correlate it with Brouillard shift. But notice one important thing. Storage modulus here changes by 3 orders of magnitude, while Brouillard shift is changing maybe like 10%. So you might say, okay, well, so, oh, this is horrible. So this is horrible, okay, also because, well, so you need super precise measurements in your Brouillard shift. But on the other hand, you can put a different mask on your face and say, oh, this is fantastic, because all of a sudden you have this huge dynamic range for your measurements, so you don't have to adjust, okay, also all the setting on your system. So how do you get to these super precision measurements? For this, we went back to 2014, and remember, okay, well, so this was the year, okay, well, so when Nobel Prize was given for super resolution imaging, and the idea is quite simple. So in nominal microscope resolution, so you get 250 nanometers, which is defined by your optics. But if you want to localize the center of mass of, say, for example, you're imaging only single molecule there, so you can define it with as great precision as you can if you have enough photons. So basically, your localization accuracy is limited only by the number of detected photons. So we looked at this and said, okay, well, so, oh, wow, okay, well, so it's absolutely the same way we can do in spectroscopy. So, and indeed, okay, well, so we tried the same idea, okay, well, so typical resolution of our spectrometer is 100 megahertz. If we detect 10,000 photons, so we get 1 megahertz spectral resolution, and it's not only, okay, well, so the number, okay, well, so it's actually, okay, well, so experimental results, which we then demonstrated and showed that indeed, okay, well, so if you take care of the stability of your laser system, so you can achieve these 100 times enhancement of spectral resolution, and this is how we do most of the measurements. Okay, so that's enough. Okay, well, so let's look at some pretty pictures, right? So those are the first experiment you can possibly do, okay, well, so with this Brouillard microscopy. It's actually, okay, so a serious experiment, and I'll explain you later. So Chinese hamster variant cells on a glass substrate. So we look at under normal microscope with some DIC contrast, so not so much you can see. So now we turn our Brouillard microscope here, and boom, okay, well, so we see some structures there, okay, well, so colorful pictures. So what do these colors mean? So essentially, okay, well, so for all the pictures that I will show, red color means stiffer, blue color means softer, and you see that the solution is soft, and some structures inside the cell are pretty stiff. So then what we can do? So we are doing 3-dimensional imaging. So what we can do, okay, well, so we can just slowly go from the bottom of the cell, okay, well, so up to the top, and you see, okay, well, so that stiffness changes. So at the bottom, where glass is interacting with those cells, you see stiffer substrate, and cells adjust to this substrate, making themselves stiffer. So outside, so we have a solution, so which is soft, and cells adjust themselves also to be soft. So we can repeat these measurements again, okay, well, so for soft gels and stiff gels, and immediately you see, okay, well, so when we turn Brouillard contrast, so we get stiffer contrast inside those stiffer hydrogels. So then, because we decided, okay, so, well, let's look at biological tissues. So methylated gelatin to gel also is important for many applications. We characterized those gels using Brouillard measurements. Then we decided to add nanoparticles to stiffen them. And here is the first problem that we found. So for the regular measured storage modulus, so we see that they increase in stiffness, but for our Brouillard measurements, we see also decrease of stiffness. And my student was repeating these experiments again and again, also, and still got to the same result. What's the problem there? So apparently, it was not the problem of our measurements, but it was the problem of structure. So by changing the concentration of these nanoparticles, we actually changed the structure, and the structural heterogeneity drives these local viscoelastic properties. So this was for tissues. Okay, well, so we also did see some very interesting experiments using subcellular imaging. In this case, we were trying to see invisible changes using microscope, Brouillard microscopy. So what does it mean? So one particular application that we were looking for, also, which was supported by Department of Defense, was looking at the nanosecond electroporation. And the idea was that, okay, well, so everyone thought that the nucleus was not disrupted by these measurements. And the way typically people look at this is just looking at cell penetration, so dye penetration inside those cells. They see, okay, well, so nothing penetrates the nucleus, but okay, well, so this dye penetrates inside the cell. So that means that external membrane is disrupted. So we combined our Raman and Brouillard microscopy together, okay, also, and see, okay, also different parts of the cell, okay, also show different stiffness. And then we focus on one particular compartment and look at time dynamics of those changes. And this is something that unusual happened. We saw that we see changes in this behavior. So cell's nucleus is affected. Cytoplasm obviously also gets affected the most because also you have significant changes in cytoskeleton. But the most important thing, also for the first time, we were able to observe that nucleus is also getting affected. I mentioned cell invasion, also, and this is a joint work with MD Anderson Cancer Center. We demonstrated that in order for cells, also, to go from this stiff core, also, which is the model for tumor, and metastase, so they first to adjust their stiffness, so that means that they become softer, also, and then, also, when they find the new spot, they become stiffer again, and this was also the new discovery. So since I mentioned morphogenesis, also, we also looked at zebrafish development. So this is zebrafish 48 hours after fertilization. You see cardiovascular system is already working there. Also, we can image it, and we moreover can watch the heart beating. So it's really, also, it's a lifetime measurement. But you see that this image also is kind of pixelated. So in order to get rid of this pixelation, we need advanced instrumentation. And one of the ways to do that is to go back to original work by Brouillard and introduce stimulated Brouillard scattering. So we did it several years ago. So we excite this acoustic wave using 2 counter-propagating pulses. So, and now, so instead of millisecond time scale, so we have microsecond time scale. So we can truly accelerate this process by orders of magnitude. So we can image things like that, but it's really also all in the glass. So if we go to the cells, so we see that cells are dying, so at the time scale of minutes, if we put too much power there. So really, so it's not only so cells are dying, but they're also changing their properties. So we did this for neuronal imaging. Apparently, so stress peripheral neurons change their mechanical properties upon any kind of stress, which can be also due to laser light. So really, so you need a new paradigm, and there is no revolution in evolution, so you need a true revolution. So For this, it's robots. For us, it's quantum light spectroscopy. And there is lots of beautiful talks on this conference about quantum light spectroscopy. I'll just point out to the major point that squeezed light, less noise, less power can be used. And you can also just skip this, okay, also for the sake of saving time. So we generated squeezed light using atomic rubidium vapors. So we routinely get 6 dBs squeezing, and we use this for this same setup for stimulated Barilla microscopy. And also this is just to convince you that we see the same type of spectrum. But here, okay, also we use squeezed light, and what happens is we don't change the amplitude of the signal, we change the background noise. It's maybe not significant when signal is strong, but when signal is weak, barely seen here, so you can easily distinguish this signal using squeezed light. So we can do spectroscopy, showing that we have a quantum advantage of more than 3-4 dBs, and we can do imaging. Okay, so in this case, we just image a glass block. So with coherent light, we pretty much see nothing. With squeezed light, we have a pretty significant contrast. And of course, okay, so glass block is not interesting. Let's image cells. So we take the same cancer cells that we imaged before, put them in hydrogel. Okay, so they are different in the umbrella spectrum, and immediately you see that with quantum light, we see significantly enhanced contrast as compared to classical light. And you can also here's another example. So we also check that photo damage is significantly reduced using quantum light. We can image the whole brain. Okay, well, so not human brain yet, but Drosophila brain. Okay, well, so which is relatively small. Once again, we see significant enhancement in contrast. And really, okay, well, so that provides us with the premise that quantum imaging is indeed great. Okay, well, so tool for biological imaging. So in summary, okay, so once again, I want to conclude with Feynman's talk. We are not to tell nature what she's gonna be, okay, well, so she's always better than us in terms of imagination, but we are trying to learn from nature. In summary, I hope to convince you that Barilla microscopy is an emerging biomedical imaging tool which has a truly unique contrast, which is non-invasive and label-free. There is a true need for Barilla microscopy because all biologists need this contrast, which they can't get by any other means. And of course, okay, also because it's mostly lazy conference, so I want to emphasize again, so quantum imaging has a great potential for biological systems because biological systems are very fragile. They can die, okay, also, and they can be affected by excessive laser power. And of course, there are plenty of things we can do, okay, also, to make things better. So finally, I want to acknowledge the funding which made this possible, and she also thanks you, okay, also, and she also, especially for students, we are looking forward to see you in College Station. We also apply for graduate positions and postdoctoral positions at Texas A&M, and we have great barbecue to offer, okay, also, and okay, also great company, okay, also, and of course, okay, also you can see us not only in visible light but also infrared as well. And Wanderley can provide cooking, and I can assist him. Well, so if you have any questions, please feel to contact me via my email. Thank you very much.
Thank you, Vlad, for the nice talk, and we can open for questions. 1, 2, 3, 4.
Thank you very much for the nice talk. So I have a question on about the last part. So if I understood correctly, what you say that using quantum light, you are able to have less power shined on the biological system, and then to reduce the potential damage by light power.
Absolutely correct. Yeah, so at the end, you want to to enhance your image contrast. Your image contrast depends on your signal to noise. So you can improve your signal to noise by increasing the power, so increasing your signal, or by reducing your noise. Squeeze light allows you to reduce your noise. This is how you improve your signal to noise, and you improve your contrast.
So I have similar question. What happens with the time to get an image when you go to the squeeze light experiment? What happens with the time of taking an image? You made a point that you want to make images fast, and when you go to squeeze light, what happens with the time per image?
So the question is how fast does it take with squeeze light? So it all depends on the conditions. So if you are fixed with a signal to noise ratio and fixed power, so you get improvement in terms of the acquisition speed. So essentially, you can get the same quality of image 10 times faster. So we have a 3 dB enhancement of signal to noise, which transfers in 10 dBs in increasing in the speed.
Thank you very much for a very interesting talk. I have two very small technical questions. One is still about timescales. You showed several timescales, but if you want to do a scan for practical applications, how long does it take for you to scan tissue or a sample, liquid sample or whatever? And the second one, I was impressed by the fact you were saying 3.4 dB squeezing. What kind of sources are you using? It's not the small squeezing.
Okay, so I will first answer the first question. So how long does it take to do the imaging? So if we do classical light imaging, so we typically get about 50 to 100 milliseconds per data point. So if we use squeeze light, so we are still keeping the power the same. So it's 10 times faster. So we can do it to about 5 milliseconds per data point. And this is in scattered tissue. So then, okay, also it depends on how many points you want to image. So you do the math. So in terms of the light source, well, so we are not using the best of the best sources. Okay, well, so if we work a little bit harder on our squeeze light source in rubidium vapors, we should be able to get 10 dBs of squeezing. We currently only have 6, so there's still work to be done. Okay, well, so, and we have some other schemes how to improve it even further.
Thank you so much for your presentation. I just have a question concerning the other label-free technique microscopy we have. Consider that you can put together polarization with confocal microscopy. What do you think will be the main challenge for you to go and apply your technique for biological tissues, considering all the scattering and the absorptions properties?
Well, there are always challenges. There are always challenges, but the great thing about Brühler microscopy is it's utilizing such a narrow spectral window so that it doesn't interfere with any other microscopy at all. So we have already shown that we can combine it with fluorescence imaging, with fluorescence lifetime imaging, with polarization microscopy, with Raman microscopy. So almost like anything that you wish to have, but now we can add additional contrast, and that's the real power of multimodal microscopy.
Okay, so we are exactly on time. So thank you very much, Vlad, for the nice talk, and let's thank Vlad again.
Use this with point.
So do you have HDMI or? Yeah. No, sir. Yeah. This is VGA.
VGA, do you have it?
So this can be.
Okay. Also this one, right?
Okay, so now we have the second plenary talk of this morning, and will be given by Len Young. She is from St. Louis, Washington University, and she's going to tell us about explore exceptional points in optical microresonator, fundamentals and applications. So, Len, please. You can use.
It is my great pleasure to be here. It's my first time to attend this conference. I feel myself like a little fish diving into a big pond. Having a chance to explore a lot of interesting, exciting research, I learn a lot. I feel myself as an outlier in this conference because you will see a lot of engineering aspect of a physical system. But I sometimes it might not be a bad idea to be an outlier. Maybe this is my opportunity. I do hope you find this research interesting and potentially find this as an interesting platform to implement and explore interesting physics. So as you can see from the title, we're going to explore an interesting phenomenon. It's called exception point in optical resonators. I will cover both fundamental science and application. In the meeting in the past few days, I already see some young faces here. So I prepared my slides in a way, it's like a tutorial that gives students a chance to learn something new. First of all, I need to mention something important to me. This is my first time coming to Brazil. Fantastic experience. Not only the beautiful thing I've seen in the past during the weekend, but also the people I interact with, the students who engage with me even before I came here to ensure everything is taken care of. They organize, make everything perfectly. I told my friends, the pizza we had last Friday evening, it just made in a not so fancy place, but it is the best pizza I have ever taken. I haven't been to Italy yet, by the way, but so far it's the best. So really great experience, and the team building event gave me a chance to know a lot of great scientists, so appreciate all those. And in addition to that, I do want to mention a little bit about my school. I came from Washington University in St. Louis. It was founded in 1853. It was a long history. And there's been 26 Nobel laureate at WashU. And a lot of great things happening at WashU. It has art and science school, engineering school, and medical school. For those of you who are interested in healthcare-related research, WashU definitely is a top choice for you. And in addition to that, and one more party I want to acknowledge is the people I have worked with, in addition to my students and those who are graduate, and they're also fantastic collaborators who contribute to many ideas that we presented in the next few slides. So first of all, let's talk about the motivation to work on optical microresonators. The many photonic system, right? For example, probably everybody know optical fiber that has been used to guide light and for this, bring information from one continent to another one. But how about some changes in the light behavior? I want to use water as an example. So in ancient times, people had already learned to use water to do mechanical work, right? But how about you turn water into steam? Chemically, still water. But now when you heat the water up, so it becomes steam, that means when an object increases temperature, everything is still the same chemically. However, the kinetic energy increase, right? That just means more energy dumped in the system. Then water can do more. It can drive piston or turn turbines, which can be used to generate electricity or propel propelled vehicles. That is fundamental change in industry process. So that is why optical resonators is a very interesting, unique structure. Think about light that has been used for communication, right? What about there's a system that can confine light in a confined volume, and light cannot escape outside, and it's confined. And we also know a phenomena is called constructed interference. If you construct such structure such a way, whenever the light finish one round trip in such structure, get back to the original position, the phase is identical with the original copy, then you will see constructed interference. Then will build up itself, right? How about you have a structure that allow light to circulate around for millions of times? There will be millions of copies. They build up itself. As you can see, power will be enhanced. a lot of interesting things will happen. For example, nonlinearity. For example, nonlinear optics was found a long time ago, but it was not boosted until laser was invented. So that is why microcavity is interesting, right? So there are many ways to build resonators. For example, as I said, if there is a way to find the light, confine light, right? The simplest way to use some light reflecting element, such as mirror, you have two mirrors, you put them side by side, so light is bounced back and forth, so you have resonators. But that is a great structure. However, if you wanted to explore microresonators, have a tiny micromirror is not easy already, not to mention you need to align them nicely. However, nature actually gave us a way to confine light in a different, beautiful, elegant way, I would say. So there was a phenomenon that was found over 100 years ago, but not in the light domain. It is an acoustic domain. So if you take a look at old paper published 1910, Lord Rayleigh already found that in the cathedral dome, the sound wave can circulate around the curved surface. So a single whisper can be heard throughout the gallery spaces. So such a structure is called whispering gallery structure. And for us physicists, sound wave, light wave, they're similar, right? They're different spectral window. So if you find a way to make a structure with circular boundary, but it's made of materials that is optical transparent, and if you find a way to couple light along the curved surface, then light wave can do similar things as acoustic wave did in the past. So that is how we form these whispering gallery resonators. So these are very simple formula telling you this condition to have construct interference, right? When the round trip of this periphery is equal to integer number wavelengths, yes, you will have this condition. That's what we call resonant condition. You will observe construct interference, a multi-copy of the light wave trapped inside. And the beauty of whispering gallery structure is it can appear in various kind of geometry, and it can be made by different materials. Can be dielectric materials like silicon, or can be interesting materials like lithium niobate. You can tune by electric current, right? And also can appear in different form as long as it has a geometry supporting this circular boundary. For example, this chip scale device can allow you to make 100 zooms on the silicon wafer. And also, the microsphere is fabricated at the fiber tip. It's like an endoscopic probe that can approach a tiny space, right? And also, for those of you who are interested in this bio application, this is a hollow microcapillary structure. You can run through the serum blood sample inside, and whispering gallery mode circulating around can detect whatever that is passing through. It's a lot of application based on your need. And before I talk about the application, I think there's a very important parameter I should talk about. So quality factor is a figure of merit we define to characterize the quality of a resonator. So it's defined as ratio of stored energy over energy lost per cycle. As you can see, if you have perfect resonator, there's no loss at all. Then the Q factor go to infinity, right? However, in reality, that is too good in reality. So in reality, there's always materials loss, for example. There's radiation loss. So with the limited loss, we write this equation. So as you can see, Q factor is proportional to photon lifetime, right? This is how this behavior. And that is true. If you measure the decay of light in the resonator, is exponential decay. From the decay time, you can measure quality factor. But there is another way to measure quality factor. If we apply Fourier transform to this equation, it will be converted in equation in frequency domain. Then let's do the measurement. Do the measurement in frequency domain. Now x-axis is frequency. And you can see here, theoretically, it tells you the line shape should be a Lorentzian line shape. That's exactly what we observed in the experiments. By measuring the line width, actually, we got a number. That number is directly related to the Q factor, inversely related to Q factor. So the narrower the line width, the higher the Q, the longer the photon lifetime. So that's how we routinely do the experiments and characterize the system in the experiments. Now we know everything. This slide tells us, not only in high Q, we will benefit a lot to make the structure small. So this is the benefit of ultra high Q microcavities. So here we define the power buildup factor as a ratio of circulating power inside the cavity versus the power you give to the system. And you can see here is proportional to the Q factor and inversely related to the size. Okay, now you see the benefit, right? The higher the Q, the smaller size, the higher the buildup factor you have. Let's do some numbers that can be achieved routinely in the lab these days. The Q factor of 10 to 8, a micro-sized cavity with 50 micron in diameter, the buildup factor can be 10 to 5. Means with input power 1 milliwatt, the circulating power inside could be 100 watt. So with those gigantic enhanced power and long photon lifetime, for example, with such a Q factor, the photon lifetime is 100 nanosecond. It is short compared to the human lifespan, right? However, think about the speed of light, 3 times 10 to 8 per meter per second. Actually, that means light can propagate for 30 meters in a tiny structure, many round trip. So with that, you will see a lot of interesting phenomena. For example, sensor application. A single molecule attached to the surface, even if it's a single molecule, but the light circulates around the entire molecule millions of times. That will introduce visible changes in the light, in the transmitted light, allow you to see things, the changes induced even by a single molecule. And there is, for example, optomechanics. Because light intensity cavity, the power is so strong, even rigid materials like a silica can be vibrated, and you can see modulation of light intensity at the transmission side. But because of limited time, I will just focus on one thing, that is non-emission physics here. So let's move on to the next slide. So non-emission physics is used to describe open system. When we talk about open system, it just refer to system with energy exchange with the environment. So there will be energy increase or decrease depending on the situation, right? And the exception point has these following characteristics. It appears in all open systems. So it doesn't matter you're dealing atomic system, a photonic system, electronic system, mechanical system, as long as you carefully control the parameter of your system, you will be able to tune the system at exception point. And once you tune the system at exception point, what do you benefit? The two interesting observations. One is you will see degeneracy. Not only degeneracy in the eigenvalue, but the eigenstates. Everything collapses in one point, eigenstate and eigenvalue. And once everything collapses in one state, at one state, it becomes very sensitive to perturbation. So that means it is a foundation to build a very sensitive sensor. And in addition to that, I want to mention in the vicinity of the exception point, the eigenvalue can be complex. What does it mean? It means the system may not be it's non-conservative. So that means the system state can, energy-wise, it can increase or decrease depending on the situation of the system. So because of this phenomenon around the exception point, it has been explored and demonstrated in various kinds of systems. Coupled resonator mechanical system and metal materials. And I will just showcase some examples to let you enjoy the beauty of this interesting physics. So let's get back to the system I'm going to talk about. Think about a circuit structure with one-gallery resonator, right? So a lot of things, like a function device has been developed based on structure and is based on an interesting property we can tune for this structure. For example, they can put nonlinear median and gain median in such a structure, right? And also, once you have one resonator, you can see the circular structure. Light can have two choices, right? Propagate or counterclockwise direction. And as long as the light is scattered in the path. And in addition to that, if you have multiple of those, let's use two examples. Then you can change the distance between them. That means you change the coupling between the two components. In addition to that, you can introduce a waveguide to couple light inside the system. Then you introduce the coupling loss, and such a coupling loss can be adjusted. It can be adjusted too. And with those parameters, you can play with. There's so many interesting phenomena you can find at a parameter you can play with. Remember, for exception point, to achieve that, you should have the capability to tune the parameters. So the more parameters found that can tune for the system, the better, because you have more degree freedom to play with your system. So let's showcase some example. I will show 3 different approaches to tune this resonant system at exception point. For case 1, the controlled parameters is loss and gain, the loss and gain balance and the coupling between those. And it just happens, this system also have a special name. It's called a PT symmetrical system. Okay, so let's, before I dive into the result, let's take a look at mathematics. Mathematics, we do the calculation, we found once the 2 resonant coupled, they will have 2 supermodes. And this eigenvalue, the omega, is described in this equation. Now you can see, gamma is used to characterize the radiation loss or coupling loss. Gamma C means coupling loss, right? And the kappa here is a coupling between them. So as long as you can see here, as long as you can tune those parameters, what you can play? You can change the sign of the numbers right here, right? If this number is positive, square root of positive number, it just give you another number, right? However, this is if it's a given number and it's a real number also. So that means you change the real part of the eigenvalue. However, if this number is negative, depending on the sign of those parameters, if it's negative, then square root of negative number is an imaginary number. So that imaginary part of the eigenvalue will be changed. So really depending on the balance of those parameters, you change either the real and or imaginary part of the eigenvalue. So what does it mean in the resonance system? Let's see how things goes. Okay, before I talk about that, let's have a brief review about PT symmetry. So in the context of quantum mechanics, if we talk about a perfect system, closed system, we use Hermitian Hamiltonian to describe it. And if you do the calculation, it will tell you energy is conserved. Eigenvalue will be real, right? However, in reality, it's not true. There's always energy exchange between the environment and the system. So for that, it's non-Hermitian, and the eigenvalue will be complex. So people ask, is it possible we find something in between? That is, it is non-Hermitian. It is open system. But can that system have real eigenvalue? Yes, it is possible. In 1998, Carl Bender, who is a physics professor at WashU, he proposed in this theoretical paper saying that, yeah, a system can be non-Hermitian, can be open, and can still have real eigenvalue as long as it is PT symmetric. What is PT symmetric? We put a condition here. The open system, if you can have a subunit in such a system so that the loss can be balanced by the gain, you can build a PT symmetric system. And for those of you who like theory, I would encourage you to read his paper. It's really fantastic. And also, I wanted to also show my appreciation to Chris Dimitri. He is really pioneer in the field. He really, I think, built a bridge between the non-Hermitian physics and the photonic system. Here's some simple explanation. So let's think about the Schrödinger equation to describe a system, right? It tells you the evolution of the system. So what about the condition for the PT symmetric? So this is the original Schrödinger equation. Under T transformation, then that means T should be reversed, right? And under P transformation, P is more like a spatial transformation. So all those variables related to spatial variable should reverse its sign. So that is T and P. How about we apply PT operator on this equation? You have the new equation, right? If we say, hey, if this is the original solution of the Schrödinger equation, we do want this we want this to be PT symmetric. So after PT operator, we have a new state, right? We want this state also to be the intrinsic state of the system. If that is true, then let's match these two equations. This can be true. This can be true as long as the potential function satisfies this condition. This is a general description for the physical system. But how to link that to the photonic system? So for photonic system, actually we can match the index profile with the potential. So if we match that, then we have conclusion for the refract index profile of the system. So what does it mean? Let's break this down to real and imaginary part. That means the real part of the refract index should be equal, right? If you change the sign of this to look at it, different space, and the imaginary part should be you have opposite sign to each other. So what does it mean? I want to use very simple case to explain how it works. So imagine a plane wave propagating along the z direction, okay? But what we also know the wave vector is affected by refract index, right? Let's rewrite it. So refract index shows up because we do want to look at how the real and imaginary part of the refract index affect everything. So when this refract index is separated by imaginary, real and imaginary part, then you will see something really interesting. The real part of refract index, is still similar to what you have seen before, right? It just modulates optic path length. However, for the imaginary part of refract index, because there is I in front of it, there's another I here, I times another I become a real number. So actually, this tells you physical meaning of the imaginary part of refract index. It tells you it depending on the sign of refract index of the imaginary part of refract index. It means it will tell you whether light will increase or decrease as they propagate. Isn't that related to loss and gain in the system? Yeah, so there is a simple illustrative way to understand the PT symmetric. So assuming you have physical system, as Carpenter mentioned, you have two units. One have loss, one have gain, right? And then under the P transformation, they switch the position, spatial transformation. And then how about time reversal transformation? For the two units have loss and gain, what does loss means? Loss means as time goes by, you lose energy. If you reverse time, of course, loss become gain, right? So under T transformation, loss become gain, gain become loss. And how about the PT symmetric? So such a system including loss and gain, under P transformation, switch the position, not the same as the initial state. However, if you apply the T transformation on top of it, it gets back to the original state. Such a system is a PT symmetric, right? It's neither P symmetric nor T symmetric, but it is PT symmetric. So this interesting system has been built, constructed in different systems: mechanical system, electronic system, and photonic system. And also even photonic system, if you dive deep in the community, there are various kind of system, like a waveguide, photonic structure, plasmonic structure, all of those has been used to develop PT symmetrical system. And I want to bring up these two pioneer experiments to show the interesting side of PT symmetric. So the top one is an experiment involving two waveguide. And on top of one of those, there's a chromium attached to the top. The chromium tip, the layer is introduced to introduce loss to one of the waveguide. So it shows, increase chromium wave, you increase loss, right? And there's another experiment that shows for this coupled waveguide, when you increase loss, initially transmission decrease as we expected. More loss will lower the transmission, right? However, after turning point, the transmission will recover. More loss actually will recover the transmission. It's opposite to what we think, right? This is one experiment. Another experiment also, again, is waveguide. So two coupled waveguide. And also, again, you tune the parameter of the system, introduce a modulated waveguide. And one interesting phenomenon shows up, that is, regardless of what input you use, the output always come up from one of the waveguide. This doesn't matter if, for example, you have two waveguide A and B. It doesn't matter which waveguide you use. Light always come out from one of the waveguide you predefined. So what is underlying reason for that? I will review that from our work to show it was also demonstrated in microresonators. To build a PT symmetric resonator, as we say, lost one and one with gain, right? And so let's take a look at these panels. So the two coupled resonators, we couple the loss gain contrast, right? And change the coupling between them. So the two panels. This shows, the x-axis shows the coupling between them. It changes the distance, changes the coupling. And the y-axis, it shows real and imaginary part of the resonance system. Now let's tell you what does it mean. The real part of the eigenvalue in the resonance system is just related to resonant frequency, as shown in the previous slide, right? Imaginary part of the eigenvalue indicate loss and gain. And from the first few slides I show, the loss and gain is indicated by the line width of the mode, right? Show up in the transmission spectrum. That's how we quantify the real and imaginary part of eigenvalue in our system. And we also compare the PT symmetric pair with the conventional coupled resonators. So the red line is conventional resonators. And you can see here, as for conventional pair, as long as you couple them together, then you're going to immediately see two supermodes. And it's two supermodes, the imaginary part is the same. That is reasonable, right? Because one slide is coupled inside. Imagine number 8. That is path experienced by the supermodes. They have the same loss, but they have different frequency because it's two different eigenvalue, supermode. However, if you operate a system at a PT symmetric regime, things are very different. After there's a turning point. So what does a turning point means? That is turning point as at this turning point, both real and imagined part of eigenvalue coalesce at one point. So exception point is a turning point, dividing the system in two different regimes. And in this regime, the behavior is very similar to conventional system, right? However, this is what we call the PT broken regime. In this broken regime, weird things happen. If you look at the real part, that means the resonant frequency, right? They are identical. So if you look at the spectrum, you'll find that, hey, maybe I just have one resonance. But if you look at the imaginary part are different. So it shows you have two supermodes, but they have the same resonant frequency, but different experience, different loss and gain. How could that be, right? Because as I said, if you think about number 8, that is an optic path experienced by supermodes. They should experience the same loss and gain, right? So that is very interesting. But before we unravel the physics, let's take a look at interesting behavior. And this is how we understand, see, imaginary part shows the light increase or decrease of the system, right? The real part is still related to the resonant frequency, shows oscillating of the field. So before we dive into the physics, let's take the system as a whole and define forward and backward direction. And we found actually, if the system is operating in a broken symmetry regime, you will see nonlinearity kicking immediately at very low threshold. So that's very interesting. And there are many reasons for the nonlinearity actually in a high Q resonator. The current nonlinearity, thermal nonlinearity, because there's again, in one of the systems, there's gain saturation, various kind of nonlinear effects. And also in 2012, Sheng Fan, he has a very nice paper talking about nonlinearity. If you have a nonlinear system, then you should be able to demonstrate non-reciprocal transmission. So we want to show that. Here is what we found. So we define the system as a black box, right? And define forward and backward direction. And we found something really interesting. If you, so for the linear regime, it doesn't matter. It doesn't matter unbroken symmetry regime or broken symmetry regime. This is a reversible transmission. However, if you operate the system in a nonlinear regime, you will see non-reciprocal light transmission. And the PT broken regime lower the threshold of nonlinearity. Okay, what does the contribution of PT broken regime? If you run the simulation, I actually found something interesting that can explain all the weird things I just explained. That is field localization. When the system is operating at a broken regime, there is a field localization as shown in the simulation. And actually that explains why the supermodes behave differently. When in the PT broken regime, right, they have the same resonant frequency, but if you look at an imaginary part, one increase, one decrease, right? So that means one experience more loss, one experience more gain. And so that means in considering the system, so one of the supermodes will be localized in this resonator with gain. Another one is localized in the one, it's like a bit sacrifice, in the lossy one. And the one localized in this resonator with gain, the light is enhanced, lower the threshold of nonlinearity, and you have a low threshold of non-reciprocal light transmission. So that is the benefit of this PT symmetric system, non-reciprocal light transmission demonstrated here. Okay, so so that's like a summary of what we found from here. And also in summary, This is just one application of the exception point in the PT symmetrical system. So in my view, I think the new things enabled by the PT symmetrical system is to inspire us to find a new approach to develop new system and materials. So GAN is not just used as a way to increase light. Instead, it is a parameter to control and tune the system. Once it's tuned into such a phase, PT symmetrical phase, then it can appear and show up with very interesting properties. So it's beyond light amplification. So the case 2, in this case, is a different parameter now. It's loss engineering. Instead of, this is a system without a GAN, and there's a system just still two coupled resonator. But in this case, we introduce a chromium tip to one of the resonators to modulate the loss into the system. Again, if you run the calculation, you can have the equation for the eigenvalue of the system, right? Again, still two supermodes. Depending on the sign of those parameters, you can change either the real or imaginary part of the system. So that is formula we used to describe the system. So this is a optical micrograph showing the two coupled resonators, and there's a chromium tip approach one of those. And let's see. So let's move on to the results. So based on the formula I just showed, right? Now we can calculate. This is panel. The real part of the eigenvalue is described in the x-axis. Y-axis give you the changes of the imaginary part. So you can see something interesting. Again, different colors is used to indicate different supermodes. Initially, when the loss is small, you have two supermodes. Those two supermodes, they have different real part, but the same imaginary part. So it means, yes, you have two supermodes, different frequency, but they experience a similar loss. That is understandable. If you rotate number 8 by 90 degrees, they experience some loss, right? However, if you further increase loss into the system, then you push the system to exception point. And once the system coupled to get to the exception point, they will pass through the system. Once they pass through exception point, it will get into a different regime. So now you can see exception point is a turning point, dividing the system in different regime. And in this regime, you can see the system still have two supermodes. But now the supermodes have the same frequency, but very different imaginary part. That means the two supermodes experience different loss and gain. But if you think about the field localization, you will see that's what it happens. So it's similar to what we found in the PT symmetrical system. So we wanted to demonstrate that this is a field localization. And we demonstrate reverse lasing, for example. In the system, initially we have lasing, right, in the system. And we increase loss. Once we couple to the other resonator, you lose the cavity because energy is distributed to another resonator. Then we introduce loss gradually to the other resonator. Because of the physics, we know that energy is gradually pushed back to the laser cavity. So laser was recovered. So it looks like contradicted to what we learned in textbook. How could loss revive the laser? But actually it does work because of physics. Because this exception point divides the system in different regime, and we can redistribute energy among the system, right? So we're not the only one exploring this. The many researchers are exploring this before us. And for the same issue, actually, there's a very interesting reviews article talking about in optic pumping, less can be more. And in addition, because of limited time, let me speed up. Talk about this more interesting phenomena. For example, one phenomenon people found about exception point is excess quantum noise. Because as we said, for conventional state, we have eigenstate, right? They're orthogonal to each other. But but when you move the system gradually to exception point, those orthogonal states will be skewed. They will collapse, finally converge to one. When they converge to one state, the noise cannot be canceled, right? You can cancel light with defined phase, but noise cannot be canceled. So when you converge the system at exception point, the noise will be carried over. You have more noise. So that being said, if you think about a laser system, is how laser was built, right? when the system, naturally system will have a lot of noise, for example, from spontaneous emission. And there is a very nice paper to explaining how to build a phonon laser. You have two coupled resonator, and one of them can generate mechanical oscillation as long as different frequency difference of the two super optical modes, as long as the difference is equal to the frequency of the mechanical mode, then you will generate a phonon laser. The reason we want to generate phonon laser because the frequency is within the range of electron spectral analyzer, so we can resolve tiny line width, small line width. And we did it. We have built a phonon laser, and we demonstrate at a certain point the line width is truly the line width become broadened, and there is excessive noise when the system is operated at a certain point. Okay, one last case. Let me use 2 minutes to finish that. So the third case is to modulate scattering in the system. So scattering, so now it's single resonators. We introduce a nanotip in the optic path to change the light scattering. And there was a paper actually, theoreticians already predict this, that there is chirality associated with every single chirality. So Whispering gallery mode is a beautiful structure to show chirality. So chirality means in such a structure means there is a directional choice for the mode. So if you look at the parameters, I tune for this 2 nanoscattera, change the relative position of 2 nanoscattera, we can tune the system at exception point. And we have experiments showing that, to show that depending on which exception point you choose for the system, the light will either propagate in direction, or clockwise direction, or counterclockwise direction, but not both. So that's another interesting phenomenon associated with exception point, that is chirality behavior of light field, and you have directional lasing. One last example using this mechanism. So again, single resonators, right, and light scatter tune the system at exception point. In 2014, the theoretician Jan Wiesig predicted, theoretically, he said, exception point sensor can be have enhanced sensitivity. And actually, we demonstrated a long time ago. In 2010, we demonstrated this whispering gallery mode. The mode can split into 2. So for example, for the waveguide coupled whispering gallery structure, right? Initially, if you look at the line in red, the single resonance. However, if there's nanoscatter in an optic path, the single resonance can split into 2. That is what we call the mode splitting, induced by nanoscatter. That is a way to detect the nanoparticle. And this is movie indicating when you introduce particle one by one on the optic path, the mode will discrete. The discrete changes in the mode splitting spectrum. And based on Young's theory, at an exception point, the sensitivity will be enhanced. And we study that. Compared with exception point sensor, the conventional sensor is called a diabolic point sensor. Probably is because the cross section is very much like the Chinese yo-yo, diabolo. It's a diabolic sensor. And if you look at the behavior initially, it's similar, right? A single resonance, but fundamentally in physics, they are different. Exception point sensor, you know, all the states coalesce at one state. So if you look at the behavior after one nanoparticle is attached to the mode volume, the amount of splitting for exception point sensor is larger, right? And then we found out actually for conventional sensor, the mode splitting scales linearly with perturbation strength. However, for exception point sensor, mode splitting scales as square root of the perturbation strength. And the beauty is, for larger perturbation, exception point sensor doesn't help. However, for a small one, think about a smaller number, smaller than 1, the square root actually is larger than the original number. That is why there's a square root rule of EP sensor can enhance sensitivity for small objects. And it's worth noting, all around the world, this is really a great community. People have demonstrated exception point enhance the sensing in various kind of system and material system. Okay, I think I have 2 minutes. So to extend, for example, one last example. So for example, this is extended version for EP sensing, right? Because for example, people may argue, hey, in my system, it's not that convenient to have some freedom to control the parameters. Can I still have a system that can benefit from EP sensing? Yes, you can. For example, in this system, we separate a random optical sensor with an EP control unit. And if you look at control unit, and we can consider, we introduce one schedule for the system, right? But the remote sensor, which can be any optical sensor, can be considered as a remote scheduler and behave remote scheduler for this control unit. So depending on the phase of this optical sensor, it will affect the behave of the effective remote scheduler and change the transmission spectrum of the EP unit. By doing that, we can effectively make use of enhanced. Yeah, we can effectively benefit EP enhanced sensing for any kind of optical sensor. Okay, I think that's all I wanted to showcase for today. There's still a lot of things that need to be, can be explored, but this is take-home message. Just our system, we already show 3 different ways to tune the system at exception point. And I bet for your system, you will have your own unique way to do that. So there, because of limited time, I wouldn't be able to showcase all the work we have done since 10 years ago, started from PT symmetrical system all the way to what I've just mentioned, the expanded version of EP enhanced sensing. And also, I want to show a summary explaining the broad impact of EP sensing. And also, it's worth noting, in addition to our own system, right, all around the world, the integrated photonics is evolving so quickly. And for example, Langfeng's group and the Massetti group in USC, they have done a lot of amazing work on using integrated photonic circuits to explore a lot of interesting things around non-Hermitian physics beyond exception point. Okay, I think that is my last slide, and now I'm ready for question.
Thank you, Lynn, for the wonderful talk. Questions?
Thank you, Professor Yang, for the great talk.
Thank you.
I want to say that you have always been my role model as a successful Asian physicist in America.
Thank you.
So my question is on the theoretical side. You show both increased quantum noise and enhanced sensitivity near the EP.
Yeah.
You know, in this community, there has been a lot of discussions recently about whether EP can really improve the shot-to-noise ratio. I know you carefully choose the word sensitivity rather than shot-to-noise ratio. And someone even argue EP cannot really improve the shot-to-noise ratio classically or quantum mechanically. So what is your stance on this point?
It's a great question. Why I say it's a great question is a question I was always asked. That is why I prepared this slide. So thanks a lot for asking that, so I didn't waste the backup slide. Yes, a lot of debate because people talk about the use. Sensing is an important application, right? So people did argue about that, and this paper is talking about there's a signal-noise ratio that cannot be enhanced fundamentally when you're in quantum regime. But when you operate system in techno-noise limited regime, it can be enhanced. But again, he still argued. I highlighted here. He said the EP sensor with the phase-sensitive gain does have advantage, even if limited by fundamental noises. So I agree, it's an open question. Actually, that is why my lab is designing experiments to explore that. Hopefully, we'll bring up and demonstrate the experimental result to showcase what's predicted by the theoretician. Yeah, that's definitely a great question. Open question we should answer. Yeah, thanks a lot.
Thank you for a wonderful presentation. So my question is more like practical side. See, so what's the optimal value for Q? Because if your Q is too large, okay, so it will be ultra sensitive to temperature, and also obviously, okay, so your light will be absorbed and heat your structure. So what's the practical value for Q?
The limitation, right? For example, the group of scientists in JPL, they demonstrate really high Q up to 10 to 11 by using the crystalline structure. So basically, they achieve Q factor fundamentally limited by materials absorption. Yeah, that is, as far as I know, is like record for Whistling gallery mode. Thank you.
Do we have more questions? now. If not, let's thank Lana again.
Thanks.